Back in chapter 3, we went over the 0-1 knapsack problem, and we used the exhaustive search technique where you had to find all the possible combinations of items that could possibly fit into the knapsack. And so, for example, let's look one more time at the exhaustive search version of this algorithm. So I'm going to write this down, exhaustive search, before we move into the dynamic programming version. So in my problem, I'm going to say that I have a backpack of capacity 10 pounds. And then I have these items. I have a shoe, which is 1 pound, worth $5, so that's its value. A pineapple, 2 pounds, $3 value. A toaster, 4 pounds, $5 value. A rack of ribs, 2 pounds, $3. And a 2-liter bottle, 5 pounds, $2. So each one of these items has a weight and a value. And so with exhaustive search, what we would do for this is we would start with the end item. So I'm going to start with this 2-liter bottle. And I'm going to say, do I want to put it in the knapsack, yes or no? If I were to say yes for item 5, so item 5, if I say yes, then that means that our capacity, which starts out at 10, is going to be, we now can only have 5 left. We have 5 pounds left over that we can use. Also, what is our current value? The value starts out at 0 of the knapsack, but if we add this Mountain Dew bottle in it, then we will have 0 plus 2, so we'd have $2 value. Now, if we were to say no, don't add the Mountain Dew bottle in, then our capacity is still 10 and our value is still 0. Okay, so once we've done that for this particular item, let me box these up. It makes it a little more clear. We then can choose about the 4th item. So either yes, I'm going to include the 4th item, or no, I'm not. And here's the thing, we're either going to have a yes or no branches for each of our previous decisions. So now we have 4 possible branches that led us to, by making some of these decisions. So I could have said yes to item 5, yes to item 4, yes to item 5, no to item 4, no to item 5, yes to item 4, no to item 5, no to item 4. And so that's our capacity, our new capacity. If we say yes to item 5 and yes to item 4, would be, it was at 5 pounds. Item 4, the baby back ribs, is 2 pounds. So we now have 3 pounds available. The value, we did have a $2 value. We're going to add the ribs at $3, 2 plus 3. So we now have a $5 value in our knapsack. And now if we said no to the ribs, but we had still said yes to the Mountain Dew, then our capacity is 5 pounds and our value is 2. It remained the same from our previous decision. Now if we said no to item 5, which was the Mountain Dew, but we say yes to the ribs, then our capacity is now 10 minus 2 pounds. So 10 minus 2 would give us 8 pounds left. And our value is 0 plus 3, so it's now 3. And if we had said no to the baby back ribs and we had previously said no to the Mountain Dew, then our capacity is still 10, our value is still 0. So we could continue on and we would have branches for the third item, and then from there we would have for the second item, and then from there from the first item. And this is an exhaustive search, and that would take a whole lot of time. So instead of doing that, we're not going to do that. Instead, we are going to do this dynamic programming algorithm design technique where we're going to store values to solutions to subproblems in a table, which will take up more space, but it'll end up getting us the solution faster with less work, fewer operations. So we create a table that's actually going to be a 2D array, and the rows are, the number of rows is the number of items that we would have. And so we should have, let's see, I want to change this to where I have a graph. Okay, so I'm going to create 5 rows. Let's see, I'll make this look nice. 5 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, like that. Close enough. Okay, and I created 10 columns. Now, why did I create 10? That's because 10 is our capacity. Okay, and I'm just creating the cells of the 2D array. And then I'm going to make this graph go away so that this is more readable. None. All right. Okay, so here is our table, 2D array, and I'm going to go through and draw in our subscripts. 1, 2, 3, 4, 3, 4, 5, 6, 7, 8, 9. Oops, I goofed. We are supposed to have an additional column, so actually it's 11. So the capacity plus 1 is how many columns we have. And actually that's the same, dang it, that's the same for the items as well. Whoops. I'll get there eventually. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. So 0, 1, 2, 3, 4, 5. So that's what we typically do, and then we have to set all the rows and the very first row and the very first column will be all initialized to 0. So that's the very first step, is to make all of these 0. I'm going to use blue. So the first row is 0. First column is 0. Now, for each of these cells, from this point forward, we're going to follow a formula. Okay, and we're going to choose one of 2 options. Okay, and one last thing before I show the 2 options is I'm calling this whole 2D table F. Okay, because this is what the book calls it. So, how do we do this calculation? So F at index I, index J. okay, is equal to, okay, so if J minus WI, so that's a weight of an item with index I, is greater than or equal to 0, then we're going to do one thing. If J minus WI is less than 0, then we're going to do a different thing. Okay, so what are we going to do if it is greater than or equal to 0? We are going to find the max of f of I minus 1 comma j, comma, and so I should draw this like an array, I think would make more sense. So this is I minus 1, and then the column index is j. So either that or V of I, that's our value of I, item I, plus f of I minus 1, j, j minus wi. So the max between those two cells, or if it is less than, then we're going to do something much easier. F of I minus 1 of j. So the row index is I minus 1, the column index is j. Okay. And we're going to do this for every cell in this table. And actually, I'm going to move this equation here below the table so we can look at it easily at the same time. And I want to be able to see the item weights and values because that's important. Okay, so we already made sure all 0 indexes are 0. We're not going to refer to those values in the table. And then the next step is we're going to go through each of the items. So when n is 1, that means item 1, in other words, the shoe, then the weight of I is going to be 1 pound, and the value of I is going to be 5, and J is equal to 1. Okay, so J is our column, and that's J is what we're starting. So I'm going to put J up at the top. It is our current column number. And I, so I should say I instead of N. We'll just do that. I, which speaks to item 1, which is that the shoe, is referring to the row. Okay, and then what we're going to do is figure out, first of all, if J minus the weight is greater than, equal to, or smaller than 0. So J, which is 1, minus the weight, which is 1, is equal to 0. So that means we're going to do this top formula here, where we say, let's see, this is f of I minus 1. So I is 1, 1 minus 1 is 0, f sub 0 sub 1, because j is 1. Or, is that a maximum value? Or is the value, which is 5, plus f of 1 minus 1 is 0 for the row, and the column is 1 minus the weight, which is 1, which is 0. F of 0, 0. So f of 0, 1 is 0. F of 0, 0 is 0, but 5 plus 0 is 5, so 5 is going to be the result. And that's what we're going to, all that work to put that 5 in cell F sub 1 sub 1. So item 1 at capacity 1. And then this is repetitive, so we would increment J. J is now 2. And we would do the same thing. So J is now 2. We're still at this first item. So the weight, the value, and I remain exactly the same. And the only difference is now we're going to try, let's see, first we'll need to make sure 2 minus 1 is just 1, which is greater than or equal to 0. So we will do this top equation here where we find the max between f of 0, f sub 0 sub 2, and then the other one is 5 plus f sub 0 sub, and that's j minus w, so 2 minus 1, which is 1. So anything with 0 in it, which is going to be this entire row, is going to be I minus 1 is always going to be 0. And you notice the entire 0 rows and columns are all 0. So for this entire row, it's going to end up being 5 all the way across because we're just going to add 5 plus 0. That's always going to be the max. So I'm going to go ahead and put 5s for everything for item 1. Okay, then we're going to add in item 2. So we're incrementing I. I is now 2, which refers to the pineapple. And so when I is 2, some of these things change. So I is 2. The weight of the pineapple is 2. The value is 3. And J will always begin at 1. And it will be incremented at each step. Okay, so the first thing we do is J, which is 1, minus the weight, which is 2. 1 minus 2 is going to be negative 1. That's smaller than 0. And so F sub 2 sub 1 is going to be f of I minus 1. I is 2 minus 1, so that's f sub 1 sub j, which is 1. So 1, 1 is 5. So we're going to place a 5 here. Okay, and then we're going to increment j. J is now 2. Oops, there we go. And so we say 2 minus the weight of our item, 2, is 0. So this time we will be doing the first equation where we find the max between two cells. So let's look, what is the first one? It's I, which is 2 minus 1, so f sub 1 sub 1. Oops, I just incremented j to 2. So f sub 1 sub 2, so 1, 2 is going to be equal to 5. And then this other one, the value, which is 3, plus f sub, that's 2 minus 1, so that's just 1. F sub 1 sub, and then j, which is 2, minus the weight. 2 minus 2 is 0. 1, 0. Okay, so 1, 0 is 0. So 3 plus 0 is 3. Well, the maximum between 5 and 3 is 5. So 5 will be what gets placed here. And let's just do one more. And then I'm going to show you, because I think you will do these steps for every single cell in this 2D array. So, whoops, J is now 3. I is still 2. Okay, so when we do 3 minus the weight, which is 2, that's going to be 1, which is greater than or equal to 0. So we find the max between F sub 2 minus 1, which is 1, sub 3, or the value, which is 3, plus F sub 2 minus 1 is 1, sub 3 minus the weight, 3 minus 2 is 1. F sub 1, 1 is going to be 5. F sub 1, 3 is 5. So 5 or 8, which is the max, 3 plus 5. So that's going to be 8. So 8 will be placed right there in that cell. So when we go through and do these steps, which would take me forever, so I'm not going to go through and do every single little cell because it's just this repetitive steps over and over, then what we will finally get, the rest of the cells in this row with index 2 that talks about item 2 is all going to be 8s. Then the next row will have 5, 5, 8, 8, 10, 10, 13, 13, 13, 13. The next row will have 5, 5, 8, 8, 11, 11, 13, 13, 16, 16. The next row will have 5, 5, 8, 8, 11, 11, 13, 13, 16, 16. So the last two rows completely repeat each other. And so what is the answer? It is in this very last cell, which is 16. So what does that mean? That means that 16 is the maximum value that we can get with these items in this backpack. So what this algorithm finds out is what's the maximum value. It doesn't find out for us which items are actually included, so just the maximum value. Okay, the analysis or time efficiency of the Knapsack dynamic programming algorithm is big O of n times c, where n is the number of items and c is the capacity or weight, which is of course much better than the exhaustive algorithm, which was 2 to the nth power.